Hey guys, this is Ms. Today is, it's April, and I think it's I don't even know what date it is. It's the 20th, April the 20th, 4/18. Okay, I'm going to go ahead and actually put that up here because I'm only doing this video in case I'm not there at school. I'm sorry I'm not there today. We've had a kind of a family emergency, so we're going to kind of review a little bit and go through the Edpuzzle that was assigned. And I'm going to have you watch a video on the demonstration that we were going to do together, and then when I get back on Tuesday, we will do it together if you don't do it together today, just in case. So anyway, you watch videos over Wednesday and Thursday about the beginning of equilibrium constants, and we talked about reversible reactions, and we talked about these two particular graphs where we had up here is this line is the reactant line, and at the beginning the concentration you have no products, so the product line was down here, no products, so the concentration was only reactants, and so the products increase over time and the reactants decrease over time, and it always starts out where there's only reactants and zero products, and then once time goes by you decrease your reactants and increase your products. Increase products, decrease reactants, and eventually they get to a point where they stop changing, and that's kind of in this area right here where it looks like an equal sign on both of them, and that's called equilibrium. When the amount of time is going by that you're changing the reactants into products equals out, the products are going back to reactants at the same rate. So what I want to do is actually stop looking at the notes and go to the Edpuzzle and go through the questions that were missed. Actually, we're going to just go through all the questions on the Edpuzzle, okay? So let me pull that up. Well, here's all my content. The first one was the introduction, so let's look at that one. We're going to look at the questions only. I'm not going to worry about watching the whole video. So the first one was just talking about this. Let me see if I can get it bigger. Yeah. This particular reaction, and I can point to this, but I can't write on it in this particular mode, by the way. So we had this over here. This was the ammonium chloride. There's ammonium, and they were kind of connected together. They're bonded together. This is not a good picture for showing that, but imagine that these two are bonded together. And it breaks down to form the ammonia and the hydrogen chloride, or hydrochloric acid, but in this case it was hydrogen chloride because it was a gas. Well, that was the forward reaction, going from left to right, just like you read, forward reaction. Well, the reverse reaction, going right to left, is these two things, the ammonia and the hydrogen chloride reformed and formed some of this ammonium chloride. And in the picture, in the video, it looked like little white crystals. Okay, we're going to continue on from there. And let's look at this particular question. All right, hold on. I think I may have to make it small. Alright, so the questions, here were the questions. Let's go back to good. Okay, I had just gone over this portion of your notes, and so hopefully you have your notes out. And here were the first two questions, and I think I need to scroll down to see them all. So here we have graph A, and there's the beginning of where you have reactants, and the beginning where you have products, and notice it says 0. It's really hard to see on my screen. It may be difficult there too. But the concentration is in molarity, moles per liter. So at the beginning we have no products, we have only reactants. Once it reaches equilibrium, and the little line that's drawn here shows you when equilibrium is reached, then the concentrations of the reactants and the products stayed the same. Same thing over here. No products at the beginning, only reactants. Once we reach equilibrium, the products concentration went up, the reactant concentration went down, but at equilibrium, when the rates going forward and backwards are now equal, the concentrations no longer change. So I asked you, which graph is favored in the reverse direction? Remember, forward is left to right, and reverse is right to left. All right, 1 second. Okay, back to this. I had to stop for just a second. Anyway, this one, which one is favored in the reverse direction? Well, this one is favored in the forward direction because Well, several things to know. If the concentration of the reactants go below the products, that's the forward direction. Just like over here, that's what we talked about in that video. If the reactant concentration stays above the products, it's favored in the reverse direction. So the one that's favored in the reverse direction is graph A, and reverse direction means going from right to left rather than left to right. So graph A was favored in the reverse direction. And then we have these here, which picture shows what it looks like before any reaction has happened. Well, I was hoping you understood that there's the divisions with these lines. At the beginning right here, that's the beginning. We just have reactants, A and B. In the middle, this is where the forward and the reverse reactions are happening, and they're trying to reach equilibrium. They're trying to reach the same rate. And then here, finally, both of them are going in the same rate, and these concentrations of the pink, the blue, the yellow, and the green dots stay the same. So which picture shows what it looks like before? Well, that's just the A and B, the one on the far left. And then here, which picture shows what it looks like when the reaction reached equilibrium and there is now a mixture of reactants and products in the flask? Well, there is a mixture here. So, but I wanted you to think through the fact that things were still working towards equilibrium, and here we have the final end where we have a mixture, and so that would be the far right. Far right. And I got them all correct. All right. So we continue on. All right, I got to go back to, for some reason I have to make it small to get to the questions. And now let's go back to big. Now, this says, what would the arrow, the big arrow, point to the left or to the right for graph B? Or graph B is favored in the forward direction. The reactants go down, the products go way up. So if it's favored in the forward direction, that's from left to right, it would point, the larger of the two arrows would point to the right. Just like over here, the larger the two arrows pointed to the right. Ta-da! Okay, good. So that was the end of the questions for this particular Ed puzzle. And so now we're going to continue on and look at the other questions on the next puzzle. So before we go to that second Ed puzzle, let's look at the notes. We came down to here. This is right after this concentration graph. Chart rather, and I showed you this general reaction and gave you the formula for the equilibrium constant, and this is really just how to figure out what the expression of the equilibrium constant is. I told you that pure liquids and solids, you always count the concentration as 1, so you substitute a 1 in there for the concentration value. But notice that the equilibrium constant is always products, and these are the products, over the reactants. And they're the reactants. Products over reactants. Products over reactants when you're doing this. And then we went through these particular questions, and hopefully you filled these in. I'm not going to go back through them. And then here all we did was, once we have this expression, now notice that this is the expression for this particular formula, or reaction. Here's the reaction right here. And these are the products. And so notice products on the top. So the concentration of the products, and it was squared. Whoops, I'm going to use, there we go, red. It was squared because of that coefficient of 2. And then it was over reactants. And here are the reactants, and they're at the bottom. And the coefficient is a 2, so it's squared down here. So products over reactants. So this was the expression. And basically expression is you creating the formula. And then I ask you to calculate the numerical value by putting in a mole for the sulfur trioxide, 1 mole, and sulfur trioxide is right there, so I put a 1 on the top. And then we put in 4 moles for sulfur dioxide, and this is sulfur dioxide, so I put a 4 in that concentration place. And we had 3.5 moles for oxygen, and oxygen was on the bottom, so I put oxygen here. So I just put in the molar values in the exact spots where the formulas were before, and I used my calculator and calculated it out. Then we went and did a few things, and one of the questions I said it was 40 million, ended up being 400 million. I just counted the zeros wrong when I double checked it. But okay, so now that brings us back to the Ed puzzle. And now what we're going to do is go through these questions. All right, so here is the formula at the top. Okay, we have the solid. Now these are the reactants, and these are the products. And it's always products over reactants. So you had to figure out which one was the expression. So first of all, in order for it to be correct, the products right here had to be on top because it's products over reactants. So that means this one could not be right because this is the reactant. There's the reactant. So that one's wrong. And this one is also wrong for the same reason. So it's either going to be this answer or this answer. One of these two, because these two have the product first. Well, if you look at this, the coefficient is a 2, so we have the squared. That's good. Okay, so we have the concentration of the first reactant, calcium, times the concentration of fluorine, and there's the coefficient of a 2, so we make that squared. Remember, coefficients become exponents. Coefficients become exponents. All right, so that's the reactants. The products, we don't have a coefficient, it's just a 1, so that's fine. All right, so is that the expression? Well, that would be, except for one minor detail. The reactant is a solid, and I just said over here, if it's a solid, and I can't scroll back up, but if it's a solid, you put a 1 in for the concentration value. So I'd have to put a 1 in this spot. And when I put a 1 in this spot, then this simplifies to just having reactants. So this is the answer for that one. All right, what about the next one? What is the equilibrium expression for this? Again, products over reactants. Those are the products, so the product has to be on the top. So it has to be this one, because this one is reactants over products. Equilibrium is products over reactants. This is the product, so it's this one. All right, I hope you're getting this. And the next one, what is the equilibrium constant for this expression? Well, products over reactants. Products, so this has to be on the top, CH4 and H2O. Well, CH4 and H2O. Now, notice that I put H2O first and then CH4. Well, that doesn't matter. We're multiplying. So 2 times 3 is the same thing as 3 times 2. So the concentration of water times the concentration of CH4, which is methane, would be the same thing as the concentration of methane times water. So products over reactants. Notice that 3 coefficient becomes the 3 exponent. Also, I didn't mention in the previous example, but all of these are gases. So none of this is going to simplify. None of this is going to go away. And this is not a pure liquid. This is a gas, okay? It's a gas. All right, now we move on to the next one. What is the equilibrium expression for this? Again, we have only gases, so it has to be products over reactants, products over reactants. So we have N2 as a product and O2. Well, this is N2 and O2. So it can't be this one because that has a reactant on top. And it can't be this one because that has the reactant on top. So it's either this one or this one. Now, what's the difference between these two? Well, this one has the 2 coefficient, and so that needs to be an exponent. There's no exponent on this one. This one has the exponent of a 2. This one also, the N2O2, has the 2 coefficient that has become the exponent. So this has to be the correct answer because this one forgot all of the exponents that come from the coefficients inside the reaction. Products over reactants. And the last one, what's the equilibrium constant for this expression? Products over reactants, this one. Again, all these are gases, so nothing's simplified. And this time I did put the coefficients in. So submit that, double check our answers. Yes, we got them all correct. Okay. So now we can continue again. I just did that one. Did I? Oh, okay. All right, let's move on. So way over here. All right, here you just watched a video about the precipitate, so I'm not going to go through this. If we have the chemicals in this for this in school, I'm planning to kind of go through them with you. All right, now what I'm going to do is pull up a couple of review sheets for you. Okay, now I hope you have this worksheet in front of you. we're going to go through these examples. Well, I'm going to go through like one of them, and I'm going to have you do the others. This should be a two-sided worksheet. The first one is called the equilibrium constant worksheet, and it's page 79. You can't see the page number on this particular scan. So all you're going to need to do is write the expression. So we're writing the expression, and basically you're going to simplify. Whenever it says write the expression, you want to simplify it, okay? So we're going to write the expression for these. I'm not going to do number 1 with you. I will go ahead and do number 2 with you. And let's see. I will do number 2 with you, but I will remind you about something on number 3. Okay, number 2, we're going to write the expression. So the equilibrium constant is going to equal and I'm going to write this just to remind you, it's always the concentration of the products divided by the concentration of the reactants. I was writing the word concentration there. So here's the products. On this side is the products. So it's that first. So we have KCl, the concentration of KCl, and the 2 has become the exponent, times the concentration of oxygen. O2 is the molecule oxygen, and the 3 has to become the 3 exponent. And then we're going to divide it by the concentration of the reactants. And so here are the reactants, okay? So we have the concentration of KClO3, that's the molecule, and we have to raise it to the 2 power. So that's the expression before it's simplified. This is not simplified. And we have to simplify it by looking at solids or pure liquids. Now, well, that's interesting. Let's see. Go away. Let's see here. Notice that this right there, that's a solid, and this is also a solid. I'm going to tell you now, look at number 3. That's water, and that is a pure liquid. And then this is in a weird font, a color, but so whatever I'm doing to the solids, you also are going to do in number 3 to the pure liquid. Whatever solids and pure liquids have a concentration value of 1 when you calculate these things. So I'm going to go through now. Wherever I see the solid, I have to put in the number 1. Wherever I see another solid, I put in the number 1. Okay? So now simplify this. 1 squared is just 1. So this is going to go away. It'd be like 1 times oxygen cubed over 1. So 1 squared is just 1. So I can simplify it even farther by saying that the equilibrium constant is only the oxygen concentration cubed. Whatever the concentration is of oxygen gas cubed is equal to the KEQ. That's the expression. Now, we're going to use these expressions in the next worksheet, so make sure your expressions are correct. What I'd like you to do now is pause the video and go ahead and let's do I want you to all right now do number 3 and number 4 and number 5. So numbers 3, 4, and 5. We're not doing number 1 because we did this one, I think, in the video already. So numbers 3, 4, and 5. Pause the video, and after you've completed that, I'm going to put up the answers for you. Okay, I hope you've done these. There's 3, 4, and 5. Go ahead and check your answers and correct them if they are not correct. You need to understand this concept. Notice that I wrote in reasons for why I did things, and AQ, I'm just reminding you that AQ, really it means dissolved in water. So something that's dissolved in water, that means you obviously do not have pure water because something's in there. So you don't put a 1 for that. But L, liquid, means the water is pure. So I put in the 1, and I end up losing that pure liquid on the bottom. Same thing down here. This one had only gases, so there was nothing to simplify. I just had to remember the exponents, and I didn't circle this one. That one's a 2 right there for you. And over here, that same thing we had. This was a solid, so for solid I had to put in the 1. And here's the coefficient of 2 that became the exponent of 2. And it's aqueous again, aqueous, dissolved in water, so it's not pure, but I could get rid of the one on the bottom. So this is the final simplified equilibrium constant. Okay, check your answers. When you're ready, we need to move forward. Okay, I'm hoping you're done. Now turn to the other side, which is called the equilibrium constant, or again, it's calculations using the equilibrium constant. This is page 80. Now what we're going to do is take the constants that you had before, and we're going to actually apply them. And I'm going to go ahead and do numbers 1 and 2 with you. And maybe I will do number 3 with you, and then let you just do the other 2 by yourself. All right, number 1, I'm going to go ahead and rewrite the equilibrium expressions. Now these were on the other side, so you could basically copy them down from page 79, copy them onto page 80, so that you'll know what to do here. All right, so here we have the expressions written in. So now we're just going to calculate the actual values. Use expression from page 79, so you're going to need to fill that in for 4 and 5, and calculate the K. That means calculate the equilibrium constant. So for ammonia, I'm going to put in 0.0100 I don't have to worry about the M, to be honest. You don't have to have this has no unit, okay? That's something we haven't mentioned. There's no units here, but I do have to square the number. For hydrogen, nitrogen rather, 0.0200, and for hydrogen 0.0200, but that's cubed. So now you just need to put all those values into your calculator. I'm pulling my calculator up, turn it on. All right, so 0.01, and I'm going to square it. So I know that y'all know how to do it differently than I do, but so that's 1 times, remember the E means times 10 to the minus 4. I'm going to divide it by 0.02, enter, that's for this first expression, and divide again by 0.02 cubed, 0.02 up here at 3. So I get 625, 625. Now that is the equilibrium constant. It's greater than 1. So remember, when the equilibrium constant is greater than 1, that means the equilibrium is going to shift to the right. This is favored in the forward direction, which is left to right. We're going to make more products than reactants. And that's what we have here. Remember, the equilibrium constant is products divided by reactants. Okay, so now let's put in the next one. We're going to just put in 0.05, and we got to cube it. Pull up my calculator. 0.05 cubed is 1.25 times 10 to the minus 4. 1.25 times 10 to the minus 4. Now, this has only one significant figure because these are leading zeros and they're losers. I do have to have the decimal there to hold that 5 in the correct position. So this would also have one sig fig, so 1 times 10 to the minus 4. That's a very small number, okay? If I wrote this in standard notation, this would be 1, 2, 3, 4. It'd be zeros right there. So it'd be 0.0001. The KEQ this time is less than 1. I'm sorry, yeah, right? Yeah, less than 1. Sorry, this is 0.0001, and that means that number is less than 1. So that means the arrow is going to point in the opposite direction. That's kind of sloppy. I apologize for that. Let me see if I can clean that up just a second so that we can understand this better. The KEQ, this is it, that's the number, is less than 1. So the arrow is going to point from the right to the left. So it's going to be favored in the reverse direction. Favored in the reverse direction. All right, this last one, we put in the values for a hydrogen ion. Now don't let the hydrogen ion concentration mess you up. It's still a concentration of a reactant, so or a product. 1 times 10 to the minus 8, and the concentration of the OH ion is 1 times 10 to the minus 6. So you're going to be dealing with scientific notation. So let's pull the calculator out. Let's put that in there. We have 1 second function. There's the double E. Negative 8 is the first one. Enter. Times 1 second function, double E, and it's negative 6. Enter. So I have 1 times 10 to the minus 14, which, if you know math, you should know that you just add the exponents together. So that's a very small number. The KEQ is still less than 1. So this is going to still be favored in the reverse direction. It's reverse. Favored in the reverse direction. Okay, I would like you to try numbers 4 and 5. You should copy your expression from the previous page. Once you have these answers complete, I want you to look at the answers on the screen and make any corrections. Alright, I hope you have your answers. This was the previous page, 79, and there's all the equilibrium constants. And this is the page we worked on together, and I did those first 3, and here's the answer to the last 2. Make your adjust your answers if you need to adjust your answers. Now, I will notice that they did not fix this for significant figures up here, but that's okay. I'm not too worried about sig figs here. It's still pretty much the same thing. Okay? All right. Now, and this one had, yeah, it only had 1 significant figure. So, okay, I hope you have that right. Now we're going to move on with the Ed puzzle. So let's go back, not the Ed puzzle, the Prezi. I did have a video I was going to watch. Now, this particular video is in the Prezi. It's one of the ones that you could watch for a review. I'm only going to have have you watch this one right now, because at the beginning of this video, he does something that we were going to do in class together. And when I get to see you again, we're going to not watch this, we're going to actually do this. So you can understand the reactants in this first jar are going to turn to products in the second jar. And then he's going to be dumping them back and forth until they reach equilibrium. And when they reach equilibrium, the forward reaction, going from reactants to products, will equal the reverse reaction, going from products to reactants, so that the amount of water he's dumping in both directions will be the same. So let's just watch this for a few minutes and watch this happen.
What I'm doing is moving water from one jar to another, and so these will represent reactants.
And I just realized something. Okay. No. That I don't think I have the sound set right, but we're going to watch this anyway and then see what happens.
Reactants and products. And you can see that as I move it from the left to the right side, I'm using a larger glass to move that water from the reactant side to the product side. But as I try to move it back to the product side, I can't quite fill that all the way up. Now this would take about 7 minutes to do, so I'm going to speed it up about 1,000 times. And so you can see that the reactants are being converted to products, some of those products back to reactants, and you might say the left side's going to empty out. But I can't quite get all the water out. So what happens is it reaches an equilibrium state, where even though I'm moving water back and forth, the amount of water that I'm moving back and forth is equal. So it's reached equilibrium. And so
okay, so that's just showing you how that works. Okay, so now let's go back to our Prezi and see where we are. Actually, I brought up your notes. So that brings us to Le Chatelier's principle, and I had planned on doing a kind of an introduction, a video, demo with you, going outside. Today would be a great day. So I'm not going to move forward with this here. I just want you to be prepared to go outside on Tuesday, Lord willing. If not, we'll do it in the main hall. So I'll see you soon if I'm not there today. Talk to you later.